All right, guys, welcome back. Today for MEGN 300, we are talking about the lock-in amplification part of your LabVIEW II assignment, and you may find this topic useful for when you do your design challenge if you're really going for trying to get the furthest distance of being able to see your reflected optical signal. There's a special type of filter that's specifically designed for this application. It's pretty neat how it uses a mathematical trick. It's called a lock-in amplifier, and let's jump into it and talk about how it works. All right, so the reason this came up, it actually came from spectroscopy, and in spectroscopy, a lot of times we use infrared spectroscopy. It's really good for identifying different molecules, especially organic molecules with carbon in them. And one area where scientists wanted to be able to use infrared spectroscopy was inside of a flame, so you could understand how combustion works, right? You can see how all the chemical reactions happening inside of a flame. Well, how do you do spectroscopy inside of a flame? So the way this works is you have an infrared light source, you shine it through whatever sample you're trying to identify and see the molecules in, and then send it over to an infrared detector. The problem here is the flame emits a ton of infrared light, like way more than the infrared light source itself actually does. So how do you see that light source and separate the light from the light source from the infrared light that's generated by the flame? And the solution that was come up with was called a lock-in amplifier. It's a special purpose filter that's designed for recovering signals from very, very noisy environments. You can do this with analog hardware, is how this is done in labs a lot of times, or you can do it through software too. All right, so what we'll be doing in your LabVIEW assignment is we're simulating one with LabVIEW so you can see how it works. And you can take that and you can set it up so that you could collect actual data and use the same algorithm inside of LabVIEW to recover your data from a noisy environment. All right, so let's talk about how this lock-in amplifier actually works. So the important key here is remember that every single signal we can represent as a series of sine waves of lots of different frequencies. So the question that scientists worked out here is, well, what if we take our signal and we make it one very specific frequency? So all of our signals is just in this one frequency, and all the noise is going to be spread out across lots of different frequencies. Can we just separate that one frequency by itself and ignore everything else that's not exactly the same frequency, right? So we go ahead and we're going to make our signal here that's just one specific sine wave. Now what we're going to do is we're going to generate a reference signal that's the exact same frequency as our original signal. Now there's a cool trig identity that happens when you multiply two sine functions together right here. So if we take our two signals, multiply them together, this is the result. And it looks big and ugly, but there's a cool effect that happens to happen right here, right? So look at that first term in the resulting trig identity where you have omega r minus omega s. So those are the frequencies of our reference and our signal that we're trying to recover. And you notice that if omega r and omega s are exactly the same, that first term is going to have a frequency of 0, which means that it turns into a DC signal or DC voltage, right? And then everything that does not have the exact same frequency, so anything that's not the exact same frequency as the reference signal, is going to be not DC. So what we can do is we can use this algorithm. We'll multiply the reference signal and then our noisy signal that we're collecting from everything else, and then run it through a low-pass filter with a very low cutoff frequency, so we just get that DC component. We'll ignore everything in the second term of this trig identity. Right? Very little of the noise is going to have the exact same frequency as our signal, so this is really good at rejecting everything except for the signal that we wanted to look at. Right, so that is the idea of how this is going to work. Let's jump over to LabVIEW. It's a little bit tricky to wrap your head around how to set this up in LabVIEW. So I'll step you through the general algorithm. We'll take a look at it, and then you can play with the VI on your own and answer the questions in your homework assignment. So let's head over to LabVIEW and talk about how to set this up. Alright guys, let's go over to LabView here, and we're going to show you how this lock-in amplifier goes together. So this is a little bit complicated to wrap your head around the first time you see it, so I'm going to give you some guidance on how to put this together in LabView. I've gone ahead and start to put some of the basic structure of the VI together. So we have our front panel, we've got a graph to see our noisy signal just before we recover it with the lock-in. This is our output here is the recovered signal amplitude. So the lock-in amplifier returns the amplitude of the original signal. And we've got some controls, so we can control the signal frequency that we're using, we can control what the signal amplitude is, and we can change the noise amplitude, so we can change our signal to noise ratio and see how effective our lock-in amplifier is. Over in the block diagram, what I have here is I've got a while loop. All right, so this is going to continuously run, and I've put in the metronome so that we can control how quickly the loop runs, so that the graphs don't update way too quickly, which makes it really hard to tell what's going on. And then we've got our numeric controls from the front panel, we've got our graph and our waveform chart. And then I've also gone ahead and I've put the simulate signal in here. This is what we're going to use to generate the original signal that we're trying to recover. So let's take a look at my settings in here. We're simulating a sine wave, right? We're going to be changing the frequency and the amplitude here, so it doesn't matter what we put into this particular window. It's going to get overwritten by the values that we put in the block diagram anyways. Key things down here is you want to change the samples per second and number of samples, right? So both of those I've set to 100,000, right? And we want to make sure that run as fast as possible is checked also, just to keep our timing correct in the VI. All right, so that's what we have in here. So this is our signal that we're trying to recover. So we're going to go ahead and put some comments in here because this is going to get a little bit messy otherwise. There's our signal, right? We also need to add noise to our signal. So the key point of a lock-in amplifier, it's really good at retrieving a signal from a very noisy environment. Okay, so what I'm going to do here is I'm going to go ahead and just copy the simulate signals block. And then we're going to come down here and we're going to change the settings in here. So what I'm going to do is we just want to make the noise in this VI here. I'm going to set this to 0, so we're no longer making a sine wave, we're just making a DC value. And I'm going to check add noise. We can use the uniform white noise. That means our noise is spread out across all frequencies. That's kind of what we want. And we'll leave the other settings the same, so then our output waveforms are going to have the correct number of data points in DT, which will be important for later on. Okay, we'll hit OK there. And we can go ahead, we'll add a comment to let us know that this is going to be our noise. Keep that track of that. And the last thing we need here is we also need our reference signal. All right, so the reference signal is just the same frequency as our original signal that we're trying to recapture from the noise. So we'll add that in here. This is going to be our reference. And there we go. So we need to set the signal frequency and amplitude. So I'm going to use our control to do that. And we can set that to our frequency. The key point here is the reference signal and the signal we're trying to recover need to be the exact same frequency for the lock-in amplifier to work. So I'm just going to take this wire and add a branch. Oop, that is not the correct one. There we go. So we've got both of these are connected to the same control, so they're going to be the exact same frequency. Our signal amplitude, we can go ahead and put that into our amplitude, simulate signal block. And then our noise amplitude has its own control on the noise block here. See, so it says noise amplitude, and we'll just connect those two together to make sure we've got the correct control going there. All right, so that is how we're going to generate our signals. So we need to take our actual signal and add the noise to it. And the cool thing about this is we can actually just add these together if we have them both in the waveform data type. So the simulate signal by default produces the dynamic data type, which is going to cause us headaches later on. So we're going to convert that straight away to a waveform, which is a single waveform. So the way we do that, so we're going to right click, we're going to scroll down to express, signal manipulation, and get the from DDT block here. And then it's going to ask us what we want to convert this to. We're going to select single waveform. We don't need an array of waveforms because we just have the one data channel coming from each of these. So single waveform, and convert that. And we will do the same to both of these as well. All right, so now we can go ahead and make our noisy signal. And the way we do that is we actually just add the noise to our signal to superimpose the noise on the signal. So we can go ahead and grab an addition block. And we will add our signal and our noise together to produce a noisy signal. Now if we want to plot the actual signal and the noise together, we can do that if we build an array of waveforms and send that to the graph. It'll plot both of those together. So there's our noisy signal, and our actual signal without the noise is right here before we do the addition. So now we're plotting the real signal and then the signal with all of its noise added to it, so we can see what it looks like on that graph there. All right, next up we can go ahead and start implementing the actual lock-in algorithm here. So the key thing here is the lock-in amplifier relies on this trig identity where we multiply the reference signal and the noisy signal together. And everything that's the exact same frequency as the reference signal is going to pass through the lock-in with a gain of 1/2, so we get half the amplitude back. And then everything that's not exactly the same frequency goes through with a gain of 0, so it gets multiplied by 0 or removed from our signal. So the key thing is we've got to multiply the reference and the noisy signal together. So we're going to get our multiplication block. And it's automatically latched on and made a wire here. We don't want that. So we're going to get our noisy signal from up here. That's going to be one of the terms in our multiplication, and then our reference signal from down here, and multiply those two together. All right, so once we do that, the resulting DC signal that we get from the trig identity is what we're after. That's what tells us our amplitude. So we need to run this through a low-pass filter with a very low cutoff frequency to get rid of all the high-frequency components, and what's left over will just be the DC component, which is half of the amplitude of our original signal, which is what we're looking for here. So we're going to get a filter. So go express, signal analysis, filter right here. Drop that down. We want a low pass filter, and we'll set our cutoff frequency in the block diagram rather than here. So we'll go ahead and just accept the default settings there. Our signal is this multiplication operation right here. Right, we're going to need a little more room, so I'm going to go ahead and expand our while loop and get the stop button out of the way. Okay, so we need to set our cutoff frequency, and the key point is it needs to be much, much lower than our signal frequency. So the way I've done that is I'm just going to take our signal frequency and multiply it by 0.0001 to get started. And you can play with that in your assignment, that value that you multiply by, and see how that affects the performance of the filter. That's one of the questions you'll be asked. So we're going to go ahead in here, weld a numeric palette, get a multiplication block, create a constant, and we're going to get our signal frequency wire, send that around there, and that becomes our cutoff frequency. All right, so we've got our our lock-in where we're multiplying the signals together, send that through the low-pass filter with a very low cutoff frequency. The filtered signal coming out here is going to come out as an array of values. We're going to want to convert the dynamic data, so we just get our array of amplitudes, and we'll take just the whole average of that to get one value coming out, which will give us the best idea of what our original signal amplitude was. Okay, so again, we're going to need to convert from the dynamic data type, so express signal manipulation from DDT just to get rid of that dynamic data type, and we'll take the default values here. We're just getting one amplitude back, so taking the default value here and taking the average of that works just fine. Okay, and we'll take the average, just under mathematics, problem stats, mean. All right, and the resulting value here should be 1/2 of our original signal amplitude. So we can just go ahead and multiply that value by 2, so we just get the original amplitude back again. Go, create a constant, 2. And this is what ultimately goes to our waveform chart that shows the resulting values. Right? So here we are. One other thing I like to do here is, if sometimes you can set your frequencies such that the filter itself will start throwing an error and it pops up and it asks you if you want to stop or continue with the VI, which can be really annoying. So one thing to make that easier to deal with is you just take the error cluster and send it to a tunnel. It just suppresses that dialog so that won't be popping up and interrupting you. You can just go and change the settings and get your VI working again. All right, so now we should have everything set so that we can try this out. This should work. So let's go to the front panel and we'll put in a signal frequency. Let's just go ahead and start with 1000 hertz to see what that looks like. We'll set our signal amplitude to 1 and our noise amplitude, let's start with 0. So we'll start with no noise just to make sure that our VI is working. So we can go ahead and run the VI. There we go. And you can see that the lock-in amplifier is telling us that our amplitude of our signal is just 1, right? So it takes it a second to get going. It does have a time response associated with it, but after that, it does a pretty good job of saying that our signal amplitude is just 1, which is what it's supposed to be. Now let's start giving it a little bit more of a challenge here. So let's go ahead and give our signal some noise. You can see this is now what our signal looks like. So this white box in here is actually our sine wave. The frequency is a little high, so that's hard to see. Let's go ahead and turn that down some so maybe it's easier for us to see. There we go. So you can see that's what it's doing, is it's generating the sine wave and it's adding noise on top of it. The lock-in tends to work better. It responds faster the higher your signal frequency is. So you can see it's working here. It's gradually working its way back to the amplitude being 1. It's just responding really slowly because our signal frequency is quite low. So let me go ahead and change that and we'll see if we can get it to respond a little bit faster. There we go. All right, and you can see that it is figuring out that the original signal amplitude was 1, which is what we were looking for. Let's start cranking up the noise amplitude a little bit. So if we double the noise, see, it's really not affecting the output from the lock-in at all. It's still able to tell that that original sine wave amplitude is 1, even if you start cranking this noise up quite high. So there we go. So our noise is 10 times the size of our signal right now. It's pretty hard to tell that the sine wave is in that original, or in that red bar there. But the lock-in amplifier is not phased at all by that. Let's go ahead and make this noise really big. There we go. Slight blip there. It's starting to notice that there's some noise, but it's still doing a really good job of recovering that original signal amplitude. So that is the way that you can go ahead and implement a lock-in filter or simulate a lock-in filter with LabVIEW, and play around with how this actually works. So this should get you started on LabVIEW assignment 2 and help you understand what's going on with that lock-in filter. As always, just come in and ask questions if you've got them.